All right, let's get you set up for Case Study '03. If you're a Sisson 5470 grad student settling in with your coffee to tackle this over the weekend, you are in the exact right place. We're going to walk through exactly what you need to know before you start. By the end of this quick overview, you'll know what real engineering problem we're solving, what specific professional skill you're building, what you need to draw on your physical sketchpad, and the single biggest misconception you are about to dismantle. Let's get to work.
Picture this scenario. A massive winter storm hits Boston, or maybe a major transit line just completely breaks down. The Emergency Operations Center urgently needs to know who can still talk to whom, or in this case, who can get to where. So you pull up the morning commute data for the Blue Bike system. What do you see? 40 stations, over 1,400 edges, and an absolute unintelligible hairball. You have all the data in the world right there on your screen, but you have absolutely zero clarity. You can't actually see the flow, and you definitely cannot make a reliable engineering recommendation based on a hairball.
And that is exactly why we're here. The specific professional skill you are building in this case study is Identify. It's one of the 4 foundational skills of this course. Identify is all about taking that messy, high-resolution relational data and framing it into a graph that actually answers a specific, concrete question. Look, the naive approach most engineers reach for is just dumping raw data into a visualizer and crossing their fingers that the answer jumps out. But the network-aware approach, the one you are mastering today, treats a network as a deliberate choice.
So before you even think about touching a keyboard or opening the software, I need you to step away from the screen. Seriously, grab your physical sketchpad and a dark navy marker. Your first assignment is to draw this network by hand at 3 entirely different zoom levels. We do this to prove that the real engineering thinking actually happens in ink. First, you'll sketch all the nodes individually. Next, you'll group them into maybe 5 to 8 categories, think local neighborhoods. And finally, you'll group those into 2 to 3 high-level buckets, like income quintiles. The software is strictly for verifying your logic later. Now, as you sketch these out, I want you to literally write down one distinct insight for each of those 3 zoom levels, right there in the margins of your notebook. You're going to notice pretty quickly that the insight popping out at the individual station level is wildly different from what you see at the neighborhood level. By actively selecting how you view the data, you're customizing your own lesson in resolution. You are proving to yourself that looking at the exact same network at different zoom levels tells entirely different engineering stories. All right, once your ink is dry, you get to jump into the interactive browser sandbox and play with the real data. This is where you get to watch that messy 40-station hairball suddenly collapse into a clean 12 by 12 neighborhood heat map. And suddenly, diagonal stickiness becomes totally visible. Then you'll aggregate it one more time into a 4 by 4 income quintile matrix. And just like that, the equity question becomes completely legible. You will literally watch a clear socioeconomic flow pattern rise right out of what used to just be a tangled mess of green lines. Which brings us to your interactive learning check. Imagine an engineer at the transit agency turns to you and asks, hey, if that raw view is just gobbledygook and totally confuses non-technical stakeholders, shouldn't we just always hide it? Should we only ever show them the aggregated versions? Is the aggregated view automatically the better, more honest deliverable? I'm not going to give you the answer here, but keep in mind that every single aggregation embeds assumptions. Neighborhood boundaries are political. Quintile cutoffs completely depend on the reference populations you choose. Think about it. A planner trying to place a single new bike dock has vastly different needs than an equity analyst studying citywide quintile flows. You'll need to weigh those competing needs against each other. You'll figure that out yourself in the lab. Once you've conquered the sandbox, it's time to code. You can fire up R with dplyr or Python with pandas, whichever you prefer. You're going to build this exact aggregation pipeline yourself, but this time on a much larger data set of 500 stations and 40,000 trips. You'll run double-node joins to pull attributes onto the edges, use group by for your neighborhoods or quintiles, and hit it with summarize to aggregate those edge weights. Honestly, if you can build this specific pipeline fluently, you can handle 80% of all network analysis on big tabular data. Now, if you only remember one thing from this entire weekend, make it this. The single biggest misconception this case study is designed to dismantle is the idea that aggregation is just some chore, or that by doing it, you're irresponsibly throwing away perfectly good data. It is the exact opposite. Aggregation is not losing data. It is choosing what to make visible. Losing detail can actually increase insight. Let that sink in.
So before you write a single line of code today, open up your notebook, look at those 3 networks you sketched, and answer this final prompt. Which specific zoom level actually supports the engineering recommendation you are trying to make? And if you happen to choose the wrong zoom level, what critical system failure are you rendering yourself completely blind to?